Welcome to Chapter 13, Lecture 5, Synchronization 1, Lock and Barriers. In this section, I would like to focus on the mechanism for synchronization. In previous section, I talked about basic idea about the concurrent programming models and memory models for the consistency of the memory models. And right here, I'm going to talk about how the processes or the threads can maintain synchronization. That means the exchange of data and also set up the waiting points to make sure that those data, when they go into the critical section, can maintain the consistency of the data in the process or thread level. First, let's look at what is critical section. A critical section actually has an entry section and an exit section. The entry section will provide the control for the thread or the process that actually can enter into the critical section. So mainly it is used to maintain the mutual exclusive access. To the critical section. So basically, two processes, they might only have one that can enter into the critical section to execute it. And then when it finishes, it signals the other one to get into. Or sometimes this one finish and then wake up this guy to go into. So basically, if there is a loop. So basically, the critical section is to maintain the consistency of the data by providing a critical section that has the mutual exclusive access. And then the exit section will signal the waiting the process or thread that wait on the critical section. So implementation of synchronization scheme including the following: disabling interrupts, bakery algorithm, spin lock, barriers, semaphore, conditional critical region, or conditional variable, and monitor. And also critical section, sometimes also called as critical region. So basically here, these few mechanisms, semaphore, conditional critical region, CCR, or conditional variable, CV, or monitor. These four mechanisms are very popular and also maybe a barrier as well. And let's look at how this works. And here, these different mechanisms are what we want to discuss for synchronization, lock, and barriers. Basically, the mechanism. And right here in the part 1, we talk about the lock and barrier, and we will discuss semaphore and different mechanisms later. Implementing synchronization. Condition synchronization with atomic reads and writes is easy. So basically, it's not hard to maintain the synchronization. You just cast each condition in form of location X contains value Y, and you keep reading X in a loop until you see what you want. And actually, this one is some sort of BD lock using a loop. Mutual exclusive is hard. So basically, you set up conditional synchronization with atomic read and write. It's not hard because you can just use a loop to guard against it. It's not really hard. But to maintain mutual exclusive access is harder. Much earlier research was devoted to figuring out how to build it from simple atomic read and write. So basically, you need to have atomic read and write, and then you actually need to build on it to actually invent the mechanism for micro exclusive. So the atomic read and write is the basic concept, and you can use the busy lock to do it. But micro exclusive access is harder. Decker is generally accredited for finding its first correct solution for two processes in the early 1960s. And Dijkstra, actually this Dijkstra is very important person. He published the version that worked for M processor in 1965. And if you know about Dijkstra algorithm, Dijkstra algorithm for what? Shortest path. If you read the algorithm, and Dijkstra also invented the semaphore mechanism. And so what is the main focus that Dijkstra has? Is actually exploring the network and trying to find a minimal path to go through a certain network for routing. And also, because of this development, he also working on whether they can have mutual exclusive access to a certain route. So wait until the data come back for critical section. So actually his contribution in communication of the data and algorithm is huge. Implementing synchronization, repeatedly reading a shared log location until it reaches certain value is known as spin or busy waiting. Spinning or busy waiting is also called as spin lock. So busy wait mutual exclusion mechanism is known as spin lock, but actually nowadays nobody is using this kind of busy scheme. The problem with spin lock is that they waste processor cycles. Synchronization mechanisms are needed that interact with a thread or process scheduler to put a process to sleep and run something else instead of spinning. Note that spin locks are still valuable for certain things and are widely used. That's old days. In particularly, it's better to spin than sleep when the expected spin time is less than the rescheduling overhead. So basically, in certain situations, you don't want to have the context switch. Those kind of the rescheduling overhead, spin lock can be used for small system. Spin lock, test and set lock. A simple test and set lock is set lock and unlock is over here. Basically, let's look at the left hand side. It set a basically left hand side is the call. It set the Boolean variable to be true, and return the indication of whether the variable was previously false or not. And given a test and set, acquiring a spin lock is always trivial. So basically, you try to test a certain lock. If it is not locked, and then I will lock it. This is called test and set. And then this one, you continue to wait here. So basically, if you test and this is not locked, you cannot get a lock, you will basically spin over here, over as a spin lock, until you have the right to set a lock, and then you will go through. And here you can put your critical section or some section that you have the mutual exclusion under it. So basically, you have a lock that's false. So procedure that you acquire lock, you try to access the lock, and you try to do test and lock. While it is locked, you do nothing and spin. And then if the lock is unreleased by some other people, some people release the lock, then you break the lock, it will go through to acquire lock. You set a lock by you. Okay, so actually this one is simple test and lock on the right hand side. The left hand side, this procedure is called the test and set lock. That's on the left hand side. But basically, you will actually not test and lock. You will actually wait until the lock is released, and then inside there you actually spin over there to check the lock, and not actually running the test and lock, set and lock. You wait until the lock is released. So embedded test and set in a loop tend to result in an acceptable amount of communication on a multiprocessor, and the cache coherence mechanism attempt to reconcile writes by multiprocessor attempting to acquire a lock. The over demand for hardware resource is called contention. To reduce the contention, the writer of synchronization library often employ test and set. So it's a new test and set lock. So what's this? Every time you try to test and set a certain lock, that lock actually is what? Is a global copy that you have a memory model, you have several processors on top of it, and each time you need to get the data from the lock global copy and try to test it, and if you can set it, you set it. So you basically access the bus too often. And this one is for this test and set lock. And for this test and set lock is, I try it once, and if it is locked by some other people, I will just spin over here. So this one I can use my local copy of the memory will be fine until somebody release it, invalidate your local copy. For example, this guy invalidate and break the lock, so you will be able to go back to try to acquire the lock. So that actually reduce the contention and actually save the in the multiprocessor cache coherent environment that actually will help you to be able to acquire a lock without the over demanding of the hardware resource and contention. Here, the last is lock, set lock, test and set and lock. That's a lock mechanism. Here we have another mechanism called barrier. This is a different kind of synchronization scheme. So each thread has its own copy of local sense. The threads share a single copy of count and sense. So basically, you set up a barrier until everybody arrive. Before everybody arrive, we can go over and continue. So basically, we have 5 tasks. We need to actually step right here and wait until the barrier being broken, and then we'll continue to do task continue point. So here, provide a synchronization point so that everybody will actually, no matter how long it takes, every task is wait for other tasks to arrive. That's called sense reversing barrier. That's actually called a barrier. So a barrier is a synchronization point. So every process will go and then stop right there and then move on together. So that's the what barrier is. So basically, there is a shared variable called counter, and it's set to be n, and there is a shared variable sense that is set to be true. And then per thread, each thread has a Boolean variable local sense. Okay, so that local sense is actually, the local sense is in the process of thread for the local copy. And then the global copy, sense is located in the main memory or something. So there are 2 copies you need to take care. And then we have this central barrier. So basically, local sense, not local sense, is actually inversion. So we have a Boolean variable local. It actually is the inverse of or not of its original value. So basically, you reset it. Each thread tackle its own sense. So, and you actually can fetch and decrement of the counter. If you actually down to 1, if you fetch and decrement of the counter that actually is only one, so it's the last one. So last arriving thread is you fetch it and you are the last one. We actually reset the counter and actually set the global sense to be true to allow all of the other process to continue. So we reset the count. So maybe the count is broken. And then otherwise, we actually go into here and repeat spin, and then until local sense is global sense. So basically, what it is you may have arrived, you may not have arrived. If basically you actually you use your local sense, you toggle it. If you are originally true, you set it to be false. So actually if it is false, and then you reverse it, and then your local copy, if you are false, and then you equals to the global copy false, then you will continue to go on. So it's just like your local copy may be true or false, or true or false, right? So this time everybody wait on true, right? Next time everybody wait on false. So it actually alternating. So each time you can have one value to maintain the sense variable. So last time everybody wait on true, so there will be a barrier. Everybody wait until its value is true. Until the next one, you actually in the between you run and you wait, and then this time is false. And if you actually arrive at the central barrier, you turn your own value and then toggle it, and you wait for the other people to actually set your value to be true, and then you go into there, and then actually other people will be get out of the this repeat BD lock area. So this is so-called the barrier mechanism. It's using the toggling local sense variable as the synchronization mechanism. And here is another algorithm called non-blocking algorithm. No lock synchronization. Suppose we wish to make a arbitrary update on a shared location, x equals a full of x. Note that this update involves at least two access to x. One is to read the old value, and the one to write the new. So basically here you need to get the old value of x and then provide the new value here. So we can protect the sequence with a lock. So basically you acquire a certain lock, and then you provide a mutual inclusion. This is critical region. And then you go into there, set it to R1, and then write to X and release. So this is a critical section. And two process or thread run this function at the same time. Actually will have the mutual inclusion synchronization problem, but this is using the lock scheme. But we can do the non-blocking algorithm by this compare and swap. So basically, you actually set the value to R1, and then you call full function for R1, set the value to R2, and then you compare and swap R1 X and R1 R2 and set it to R2. So the compare and swap is a universal primitive for single location atomic update. A similar primitive is known as load link and store condition. So here are a instruction that is available on MIPS Alpha and PowerPC processors. And here, so it provide a mechanism. So if R2 is not, so compare if R1 and R2, and you will swap the R1 and R2, and if the value you compare is X, you try to access the X variable, and if your R1 and R2 actually you will try to swap the actually here you call the function, you get the R2. So here you have the x set to R1, and then you set a value for R2, and then actually set to x. So actually x value and R1 are kind of swapping, and then you set a value to R2. You compare whether R1 and R2 are the same. If not the same, you actually will go to start and go back to BG lock on here until R2 is true. Then you go into here. So R2 is the result for the compare and swap. And if it is set to be 0, then you will go back to loopback. And if it's the same, you get the right value, you actually will go into there. So basically, this is a mechanism called compare and swap. And it's a non-blocking mechanism, so there's no lock involved. So you will actually sometimes use this compare destination. You have destination command, compare value, and then swap value, and then you compare value with the destination. If the destination x is the same with the compare value, you do the swapping. Otherwise, the destination will be unchanged. So this is the mechanism for compare and swap, and it is used for as a non-locking mechanism. So it says you compare the value. Operation on non-blocking concurrent queue. In the DQ operation, left, this one DQ operation, we have these. A single compare and swap swings the head pointer to the next node in the queue. So you actually will change to here if you want to DQ, okay? And the in queue on the right, the first one, in queue on the right, you actually put something in the queue. You have to actually allow it to advance to the next one, the new node, so which point to operation to have a logical complete. So subsequent cleanup tasks, which can be performed by another thread, swing the tail pointer to the new one. So basically, by swapping, you set the so-called null to the next one. So you can actually move the tail to there by swapping the head tail to the new value. So cast function is used for that you actually to set a certain value, and also being used in many situations. So basically, compare and swap function, it will provide you some value, and if the value is like x, you will actually set the value to x, and then that's the swap value. You swap the value of the R2 to actually to cast, and then original value will be set to, after the compare result, you actually set R2 to be true or false. If it is 0, actually you will loop back. So memory consistency model. If we have a multiprocessor environment, we have cache like this, and then we have core 1 as one process, core B another process, and then we inspect. If, for example, our inspected equals true, then it will go continue, and then we'll set x value to SA, and then if we inspect it equal false, initially our x equals 0, and then our core B set the x to be 1, and then IB, the inspection B, will be assigned by inspect the value that will be false. So this one actually initially our x and y set to be 0, and then our core 1 set to be 1, core B set to be 1, and then our core C will get this value for x and y, and core D got y and x for dx dy. So here is some sort of mechanism to maintain the consistency for memory model. We have talked about the write through, p bus, write back, and write embedded mechanism. Here, I think that the author's view for this is actually complicated. So it needs you until you swap the value, you invalidate it through a bus. But normally, this is not a language for computer architects language. You just follow the write through, p bus, write back. It's its own mathematical model that it provides. Synchronization mechanism 2, scheduler lock. Scheduler implementation of synchronization. Disable time scheduler lock. Get the exclusive access to scheduler. To implement user-level thread, operation system level processes must synchronize access to the ready list and condition queue, generally by means of spinning. And call for a simple re-entrant thread scheduler appear in later slides. As in the code, we disable the timer signal before entering scheduler code to protect the ready list and condition queue from concurrent process by a process and its own signal scheduler. Our code assumes a single low-level lock, scheduler lock, that protects the entire scheduler. By saving its context block on the queue, a thread must acquire the scheduler lock. It must then release the lock after returning from the scheduler. Here, the article is very abstract. So let's look at other slides. So basically, let's look at the pseudocode. We have a rescheduling. And what is scheduler lock? Scheduler lock actually is you have multiple processes. And then you actually, only one of them will be scheduled to use the CPU. So since you have the only access to the CPU, other processes will be disabled. So the scheduler itself is actually a synchronization scheme. So that's what it is. But before we enter into the rescheduling, you need to disable the timer signal. Otherwise, the timer may kick out the process that in the scheduler. So that's the idea of what this whole thing is talking about. It's not that hard. You use your process scheduler. So every process has its own copy of current thread. There is a single thread scheduler, so that's the scheduler lock, and the single ready list. So everybody waiting for the scheduling. So basically, you need to think about I'm sorry. Basically, you need to think about it as a queue. We call it ready list. And the ready list may have one that's being picked into the service. So that if I finish, I'll call the rescheduling to wake up everybody in the ready list to compete for the resource. Okay, so it's a spin and yield lock. So our reschedule algorithm is that, for example, I'm actually right now I'm waiting. I have the control for the CPU. Then actually I declare a T as a thread. So I take the thread from DQ from my queue for whatever is available, waiting for my for the CPU to access. If it is no and do nothing, else you wait for a thread to become runnable. So you pick one and then become available, and then release the scheduler lock. And then actually you retire one process, and then you acquire it. When you get a lock, you transfer the control to T to the thread. That's called rescheduling. So window allow another thread to access the ready list. So here we actually is the lock, and to yield, you actually disable that. You give your CPU, you actually disable signals and acquire the scheduler lock and the in queue. Your current thread put into the queue, and then you reschedule to give up your control and give away to other process, and then you release the lock. Release that means that you get out of the resource. So here acquire lock, there's a loop. So you actually loop back to acquire lock. So this one yielding part is you wait for the access for critical section. And then this one actually rescheduling, you release it and enter into it, and then you acquire. So it's locked like this. So usually you are waiting here. You're waiting here, and then this one it actually will acquire lock. So this one, when it release on the yield side, when it actually release, I'm sorry. When it is released, it will signal. I'm sorry. How come it actually keep moving? So when it is released, it actually signal this guy, and then it will go back to here to release lock, and then you enter into here, and then you will signal this guy to wake up and go get a lock. Thread on queue is actually put your current thread into a queue, and then you put in there, and then you actually keep up your control. Scheduler implementation of synchronization. Disable the scheduler lock. The call for yield implementation synchronization itself because it works as a self-contained. The call for sleep cannot because a thread must generally check a condition and block if necessary as a single atomic operation. So here, call for sleep if it needs the scheduler lock. So it actually has a procedure like this to sleep on. So you need to have the mutual exclusion for getting into the scheduler lock in order to get into this sleep procedure. Scheduler implementation of the synchronization bounded buffer. Bounded buffer is a commonly used example to explain this synchronization scheme because bounded buffer is actually a producer-consumer model. So a bounded buffer is a concurrent queue of limited size into which producer thread insert data and from which consumer thread remove data. So you have the input and you have the pop and push. So this is a pop part, this is a push part. You actually can get data, but this is actually a bounded buffer in the 5.4 format. So you keep feeding your data into in, and then there's the other end to get out the data from the out part. And actually each time you have the concurrent queue, so you only allow the producer or consumer, only one side can get access to this buffer, this bounded buffer. So a correct implementation of bounded buffer requires atomic operation and the condition synchronization. The former ensures that no thread sees the buffer in an inconsistent state in the middle of some other thread's operation. The latter forces the consumer to wait when the buffer is empty and the producer to wait until the buffer when the buffer is full. So start imaging a unbounded buffer. A producer writes data to buffer. So if the buffer is not full, the producer will be able to go into there and fill the data in. But if it is full, then the producer will wait until the consumer to take out data from out. But if the consumer see the buffer to be empty, I have nothing to take out, so the consumer will wait on the bounded buffer until the producer puts something into the bounded buffer before my consumer can take out something. So that actually is a bounded buffer is a great example for producer-consumer model, and it actually can use the scheduler lock to provide the synchronization. So two things: one is atomicity, that you actually have one operation, and then you need to have a conditional synchronization. Scheduler-based synchronization. The problem with speedy waiting synchronization is that it consumes processor cycles that therefore are available for other computation. Speedy waiting mechanism makes sense only if one had nothing better to do with the current processor. Second, the expected wait time is less. Okay, and actually the overhead is smaller than the scheduler. Scheduler, you need to have context switch. To ensure acceptable performance on system, most concurrent programming language employ scheduler-based. That's actually more systematic, but the B-day waiting part actually the code will be simpler, and it's actually wasting time. The following subsection we consider Semaphore the most common form of scheduler-based synchronization. In the lecture about language mechanism, we consider higher level of notion of monitor, conditional critical region, and the transactional memory. We will talk about all of these mechanisms. In each case, scheduler-based synchronization mechanism remove the waiting thread from scheduler's ready list, returning it only when awaited condition is true. So scheduler-based synchronization is level dependent. It is specific to stress when implemented in the language runtime system. So here we just talk about the different new mechanism we are going to introduce: the semaphore, the monitor, the critical condition region, and the transactional memory. And in this current section, we talk about the scheduler-based synchronization. And previous lecture, we talked about the busy waiting lock and spin locks. So each different mechanism have different implementation. Some pretty simple but with CPU time. Some pretty decent and complicated, but it actually take more memory and waste more overhead. Synchronization 3, Semaphore, and Semaphore is the most common way of setting up the critical section, and it actually, because of the size of the buffer or queue for the waiting, so it actually can allow multiple entrants to the critical section. Implementing synchronization, Semaphore were the first proposed scheduler-based synchronization scheme, and it is remained widely used. Conditional critical region and monitors came later. Monitor has a higher level mechanism. For example, Java language is implementing the monitor. A monitor can be used to implement the semaphore, and semaphore can be used to implement the monitor as well. And synchronization in Java is sort of a hybrid of the monitor and the critical region. The conditional critical region is a hybrid. And shared memory synchronization in 885 is another hybrid as well. So right here, we talk about the semaphore first. A semaphore is a specific counter. What is the purpose of a counter? The purpose of a counter is to maintain the consistency of the critical region. At most, we can allow how many processes to enter into the critical section. That depends on how many service units are allocated in the service in the critical region. So it actually has an initial value and the two operation P and V. And the P and V operation is actually original name used for the semaphore by Dijkstra. And basically P and V, basically P and V actually is one is signal and the other one is weight. Okay, and basically here are two functions. One is weight, one is signal. So we will explain the P and V later. So semaphore keep track of the difference between the number of P and V operations that have occurred. A P operation is delayed, so usually it's a wait until number of P, the waiting one, minus the number of the V1 is less than equal to C, and that is the initial value. C, you can see it as a capacity that how many actually the process can enter into the critical section. So the waiting one, if less than the ready one, the signal one, then you can enter into it. So here we have a scheduler, EO, and the slip-on. This one is a pseudocode for the re-entrant scheduler. So a possible implementation is shown in the next slide. So here is a semaphore. Semaphore operation for use with scheduler code. So basically we have several threads competing for the semaphore. For example, right here we have share resource at most 6 seats. So we will have a synchronized P function. P function will reduce the S. S is the variable of the count for the available seat. So P function actually is weight. V function is the signal. So basically we have the semaphore. N is the integer, is the capacity. Q is the people's for different tasks to be waiting on. So the P function actually you test on a certain semaphore, store the signal, acquire the scheduler, and if the number is greater than 0, you decrease it. So you wait on it. Otherwise, if the number is already 0, then you will sleep on the as the QQ is the thread. It just Q the thread, so you will sleep on the thread until somebody wake you up for rescheduling. So you actually wait here and you get out of the scheduler lock. So P actually is a critical session to get the mutual exclusive access to your SN. And so here actually is a semaphore itself using a scheduler lock to implement it. And the function will be basically maintaining the consistency of the SN, maintaining the S right here in P function. So the synchronized will actually implement this P function mechanism. So V is actually signal, P is actually weight. So when you signal, you actually is about to access the critical region. So you acquire the scheduler lock, and then you, if the queue is not empty, you actually put that the current process into the queue. Actually, you actually wake up somebody from the waiting queue to ready list, and then otherwise you actually increase the number of the available server, and you actually re-enable the signal, so allow system to wake up. So P function is wait, and V function is actually signal. So we have a wait and signal pair for the semaphore, and we will see how the PV work later. So mutual exclusion in Java In Java, the mutual inclusion is actually have the mutual inclusive mutex. Mutex is a mutual inclusive lock. So basically, your thread can wait on mutex. And every Java object has a monitor. And at most, one thread on the monitor at a given time. A thread becomes the owner of an object's monitor, and it will be able to enter into the synchronized function. So here we have the synchronized function called increment that will increase the s value, and actually this same function can be written in this format. So this is the current object, and this one is actually a different way of writing the synchronized function. And this one is to synchronize waiting on the current object to be available. So two are actually equivalent. So a thread is actually executing an object method called synchronized, executing a block that is synchronized on the object. So that actually this one is this one, and this one is the method that actually takes synchronize. Either way, you have the mutual inclusive access to this. So that's a mutex. Mutex are built into every Java's object. Semaphore-based code for bounded buffer. So basically, right-hand side is a bounded buffer, and it actually is using the semaphore, a PV function. So basically, here you are waiting for the insert. Insert is actually the producer. So you actually will have a pair of PMV over here, and another PMV on the mutex inside here. So the mutex is actually maintain the consistency of these, the buffer and the next buffer. So basically, if you have the data, you wait for the empty slot. So if there's no empty slot, you cannot enter into that. Once you have an empty slot, you make sure that nobody is competing with you to compete for the access of the buffer and the next buffer pointer for insertion of the memory. So you basically, it's like this. Your next empty is point to here. So your data D will be filled in. After that, you advance your next empty for the next one. And right here is different. For the remove function, you actually get some data from here. You get it out for the data that you want to return. And actually, after that, you put the fail pointer to the next one. The full pointer, next full pointer to the next one. And it also, for this wave function, V function, it also has this full slot waiting. So if it is full, you cannot actually, if it is full, you actually wait on the full function, and then you signal for the empty slot. Okay, so here is the signal part using the remove function using the V function. So the comparison between mutex and the semaphore. Mutex, you can think about it as a lock. So some parts slower than semaphore, and only thread can own mutex. Available only with mutex, and primary purpose of mutex is to be used for mutual inclusion. And it actually have only one can enter into the critical section. And Semaphore is different. Semaphore can allow more process to enter into the critical section at the same time, which is under certain capacity. And event notification do not use mutex for this purpose. And Semaphore you can perform with the Semaphore for the event notification. Thread suspension. Thread can suspend if another thread already owns a mutex. And for Semaphore, thread can suspend if the value of counting Semaphore is 0. So it's possible that you can, if it is the counting Semaphore is 0, you can no longer advance. You need to wait until someone to release the resource. So here is the comparison between Semaphore and mutex. And mutex can be used to implement Semaphore. Implementing synchronization, it is generally assumed that Semaphore are fair, and in a sense that process complete P operation in the same order that they start them. So problem with Semaphore is pretty low level. That's one problem. When using them for mutual inclusion, for example, it's easy to forget a P or V, especially when they don't occur strictly a match pair. So actually, you have a signal and lock and wait function spread out in different locations. You actually have no way to really know which one should be waiting, which one should be signaling to other people. And they are used in scatter all over the places. So two problem, two low level, and scale over to different places. Difficult to spot where they are.
Lecture 8, Language Level Mechanism 1, Part 8, Monitor Definition. In this language level mechanism 1, we will talk about monitor, and we have two parts, Part A and Part B. Let's get started. First, let's look at the semaphore. Semaphore's weakness. Semaphore is a set of the mechanism that help you to set up the critical section and with certain number of the seats. So different process or thread can enter into the critical section. But it is a complex patterns of resource usage. So it is not easy to trace, especially when your semaphore statements scattered at different locations. So semaphore has limited seats, not an expandable queue. That's one limitation. Second, it's hard to trace back the code. Cannot capture relationship only with semaphores. Need extra state variables to record information, not a class. So it actually need extra variable, not actually tracking for certain class. And make sure that class is well guarded by critical sections. So semaphore has its limitation. So use semaphores such that one is for mutual inclusion around the state variables, that is the counters. One for each class waiting is hard to debug. So these are the weaknesses for semaphore. So in language level, we want to have something that's easier to use and that has the expandable queue, so you can allow many of the elements to get in. Many of the many threads to get into the critical section, to wait on the critical section. So monitor is a language level construct to help you to solve these problems. But in fact, semaphore and monitors are actually very close. Some monitor can be implemented by semaphore, and actually semaphore sometimes can be implemented by monitor, but it's actually a waste of time. Usually semaphore structure is easier, monitors are more complicated. So usually semaphore is used to implement monitors, and with monitors you can achieve a lot of different things. So semaphore is only a synchronization scheme that actually create a critical session and the management of the critical session with certain capacity and number of seats to allow different threads to get in. While monitor is a shared data class with operations and synchronization scheme, so monitor is a class with methods, and those methods can be implemented with synchronization schemes, and these synchronization schemes are born with the classes. A programming language construct that supports controlled access to shared data. This is the definition for monitors. Synchronization code added by compiler enforced at the runtime. Why does this help? So why does this really help with the monitors? Monitor is a software module that encapsulates a shared data class. So it's a shared data class with synchronization. So it encapsulates shared data structure, procedures that operate on shared data. So these are default setting for classes. And then they have a standard synchronization scheme between concurrent processes that invokes those procedures. So this is new, added to the classes. Monitor protects the data from unstructured access, guarantee only a data through procedures, hence in legitimate way. So it's a legal way to do that. Now, let's look at the Java monitor. Java has data class, and every data class can be a monitor. So synchronized data class can also be implemented by condition variable. This can be implemented by condition variable or can be implemented by semaphore, but that's implementation issue. Now let's look at how to use it first. So for thread competing with resource, we have task 1 and task 2. And in task 1, we actually synchronize certain object. And this synchronized object actually is a shared data with operation and the wait and notified methods defined inside an object. So this an object actually is a object of certain class. So we synchronize on this object, and then we try listen. And this one actually, while condition not met, we wait on it. So basically, here you are waiting for the entrance to the critical session, and here, when the condition is true, this is the critical session part. And this one actually is the one that will make the condition happen. Once it happens, you actually will notify it, and this process will resume. So this become a pair of the signal and wait pair, and you can have the cross signal and wait pair to create a critical session. So this is the way of synchronization in between the data classes or tasks. And this task can be measured in a certain thread. So wait and signal, notify, and the notify all are used in Java. It can be PV or wait signal in other languages. So these are the methods that have been defined in all the classes. And this is one example of two different methods in a runnable thread. How can they have the very low level synchronization? So example of using monitors, since we have the wait and signal, so we actually can use the consumer producer model. So this side, it actually, when this is capacity, we will actually if it is count is capacity, this side is actually the producer. If it is full, then you cannot edit. So you need to wait until not full happen. And actually, if the consumer side actually consumes certain integer from buffer, we will signal it, and then it will get into the buffer. And if it is consuming, if it added one element in, then it will signal the consumer to start to consume. So this is actually the producer-consumer model in Java format. And the signal and await this different function name, you have to check the mechanism. There are several mechanisms in Java. So now let's look at the schematic view of monitors. So a monitor has the shared data and operation, just like any class. We have shared data, we have operation, and we have initialization call, that's the constructor. And these are the standard way of a class. But what's different is the entry queue that is new to monitors. And monitor is an object which added mutually exclusive access feature. That is, you have those different methods, and also you have this queue. And stress queue is in OS or in Java virtual machine. Remember that we had a 2-level implementation and maybe 1-level implementation. So it all depends on what platform you are talking about and what is the implementation of the virtual machine or languages virtual machine, like Java virtual machine or Python virtual machine. It depends on the language. So not in monitor itself, it actually created by the Synchronized in Java's case, and Q is in OS. And I'm sorry, Q can be in OS or Java virtual machine, depending on which level you are talking about. Actually, we talk about a 2-level implementation or 1-level implementation. It depends on the implementation. Language level mechanism monitors history. They were suggested by Edgar W. Dijkstra, and Dijkstra is a famous person, developed more thoroughly by Rich Hansen, and formalized nicely by Tony Hoare, a real cooperative effort. So it's not only one person or one certain invention. It actually are actually like a torch carried from one person to another, actually through many years to finish the language monitor. And several parallel programming languages have incorporated monitor as their fundamental synchronized scheme, non-incorporate a precise semantic of Hoare's formalization. So Tony Hoare's version is very successful, but in fact, not every implementation will be 100% precise semantic of the Hoare's formalization. But Hoare's design will still be very valuable to study. Language level mechanism. A monitor is a shared object with operations, internal states, and a number of condition queue. Only one operation of a given monitor may be active at a given point of time. A process that calls a busy monitor is delayed until the monitor is free on behalf of its calling process. Any operation may suspend itself by waiting on a condition. So there is a waiting queue, and if you don't have the condition met, you have to be waiting for it, and your cell will be hanged in the process queue that wait on the condition. An operation may also signal a condition, in which case one of the waiting process is resumed. So it will signal somebody else to wake up. Usually the one in the wait list, the one that wait longest or on the first prioritized position in the wait list. Language level mechanism. The precise semantic of mutual exclusion in monitor are the subject of considerable dispute. Hoare's original proposal remained the clearest and most carefully described conditions. So these are the mutual exclusion for the monitors that described by Hoare. It specifies 2 bookkeeping queue for each monitor, an entry queue and a urgent queue. So there's an entry queue and an urgent queue. When the process is queued, a signal operation from within a monitor, it waits in the monitor's urgent queue and the first process on the appropriate condition queue, but obtain the control of the monitor. So you enter into the critical session. When a process leaves a monitor, it unlocks the first process on the urgent queue, or the urgent queue is empty. It unblocks the first process on the entry queue is dead. So right here, it is a diagram for the this monitor. So we have the data object that we would like to associate with this monitor, and we have a special room. This one actually is accessing the data, and there is a wait set and there is an entry set. So this is like a doctor's treating room, and we have a lobby over here, and there is a person that actually being treated. So it's in critical session access controlled by mutual exclusive or mutex lock. So it is in here, and there are a certain people waiting, and they have been called by the nurse or the register that you are in the ready queue or wait list queue. And there are certain people, they have not been called by the nurse or the register, that you have not been admitted to the waiting list yet. So these are the three levels of the processes or threads. So first you need to enter into the clinic, and then you got called by the nurse or somebody who handled the administration, and then you got admitted to the wait set until you have the first prioritized. Then you got sent to the treatment room or the special room. So that is the way monitor works. It works similar to this doctor's situation. And more precisely, actually, you should use this one or this one to look at it. So basically, a monitor enters a ready queue, and actually it lock, and it actually sometimes will wait and go into the waiting queue. So this waiting queue is here, and then you actually, when you got the call, you go into the ready queue until you actually got call, and you got service. So these are the state diagram for this. Language level mechanism. Building the correct monitor requires that one thing about monitor invariance. The monitor invariant is a predicate that captures the notion the state of the monitor is consistent. It needs to be truly initial and at monitor exit. So the number greater or equal to 0, number of items greater or equal to 0, and less than the buffer size. So there are certain things you need to take care of. It also needs to be true that every wait statement. It also needs to be true at every wait statement. In horizontal formulation, need to be true every signal operation as well, since some other process may immediately run. Horst's definition of monitor in terms of semaphore make clear that semaphore can do anything monitor can do. So right here, as I show you, monitor can do everything that, semaphore can do everything that monitor can do, and vice versa, monitor can do everything semaphore can do. The verse is also true. It is trivial to build a semaphore from monitor, and that makes no sense. But to build monitor from semaphore makes more sense. But two, in terms of management power, they are the same. But monitor tends to be more easy to use and with more language definition constructs. So it actually well defined, but actually easier to use, but take more spaces. Semaphore is easier, but less definition and not easy to use. Right here, let's look at the bounded buffer case with monitor. So this is a monitor-based call for bounded buffer. So bounded buffer, we have talked about this already. It has the out index and in index, and then it will add something into the in location for empty spot, and then it will take data out from the out index spot. So right here we have the monitor, and this monitor class is bounded buffer, and we have the B data, that is the data to be taken out, and the size of the bounded buffer. So we declare this bounded buffer data of this array that actually is the B data is a type. So we have the full and empty setting initial condition, full slot and empty slot condition. These are Boolean variable, just like what we talk about using the Semaphore to implement the bounded buffer. The only difference is right here you have to wait for the bounded buffer. So this is the monitor. Other than that, it is similar, but it actually uses this wait and signal mechanism in this bounded buffer. And when it remove, it uses this wait and signal, and actually you will return after you signal the the other process, and then you take out the data. So here we have the insert and remove, and it is using the wait and signal pair for the bounded buffer in monitor. And let's compare this with the Semaphore version. The Semaphore version actually has the insert and remove, and it has this P and V function. P is getting the mutual exclusive pair, and the empty slot and full slot. These two has the counter, and the counter set to 1 initially, so only one would be able to get into the critical section set up by this P and V function. And P is the entrance of the critical section. V is the exit of the critical section. So it actually will have the scattered pair everywhere. You can think about this as wait and signal, but it actually is more complicated. You can use the monitor wait and signal to implement this as well. But actually right here, it actually is the entrance and the exit pair, so it is more complicated. Let's compare with this Semaphore monitor. Sorry. This monitor version actually is easier. If the actually the full slot is equal size, that means you can no longer insert, so you wait for the empty slot. And then if there is a certain empty slot happening, you go in and put the data in. And then you increase the number of the full slot. And then you signal the full slot so that this consumer side can wake up. So this remove for consumer side, actually, it will also wait if there's no full slot, then there's no data in the bounded buffer. You have to wait until you have some data in, and then you take it out, and you signal the producer side, the insert function, that you actually take out everything. You can take out something, and then you can insert some data in. So these are pairs of the producer and consumer pair. But in fact, this bounded buffer can be implemented by both Semaphore and the monitors. Now, I'm going to talk about language level mechanism Part 1. Part B for monitor implementation. In this lecture, we will talk about semaphore, condition variable, and the monitor. These three are very close, and actually one can implement the other two. So they are closely related. So we actually talk about these different implementation issues together for semaphore, monitor, and condition variable, but they have slightly different feature and different purpose. First, let's look at the implementation for semaphore. The usage of semaphore is like this. You declare a new semaphore mutual exclusive access. Then you can have the wait and signal for the mutual exclusive access, and then you enter into some critical section. This is the use for semaphore. That's easy. To implement that, you actually can implement the wait function with certain semaphore variable, and actually if it is not less than, and if it is less than equal to 0, no, you have no up, and you actually busy waiting here until you got some seed, and then you decrease it and you enter into the critical section. And the signal part, you actually, when somebody will leave the critical section, you can actually increase the number of seats available. So these are actually quite simple. So S of count, keep track of how many remaining seats allowed to enter into critical section. Initial condition of S, keep track of the maximum number of seats in the critical section. That's the capacity. So semaphore is designed with certain capacity. Wait and signal are not allowed. Wait and signal are not always paired. Maybe signal executed. Maybe more signal executed than wait. Then the maximum number of seats will be increased. Monitor. Now let's look at monitor. Monitor can be implemented by semaphore, and monitor is a program concept or data structure concept, and semaphore is a data synchronization concept. So they actually are different. And semaphore can be used to implement the monitor. And the monitor would have these following different global variables: mutual exclusive, next, and next come. Mutual exclusive is a semaphore that initialized to 2 to 1. So it only allows the capacity of 1 to enter into the critical section. It is used to control the number of processes allowed in the monitor, the critical section. So let's go back to the previous lecture. For this chart, actually, that mutual exclusive count will be the capacity in the spatial room. And we have a next, and this next semaphore is initialized to 0. And remember that we may have more signal than wait. So this number can increase. It is used for the waiting queue by the process that are in the monitor after being released from a conditions queue by signal operation. So this is the waiting queue. And this waiting queue is the one in this wait set. And the next one is next count. It is a integer variable initialized to 0. It counts the number of processes sleep on the next semaphore. So it is always equal to the number of processes executing the monitor operations minus 1. So it's from 0 to what? To n minus 1. This is complicated. This is a complex way of saying that only one process at one time can be actively executing within the monitor operation. This is called the active process. The processes waiting on the next is the inactive processes. And to implement a monitor using semaphore, we can have the entrance call like this. We will have the waiting for the mutual exclusive function or entrance of the semaphore function for mutual exclusive semaphore. This is the entrance call when starting execution of a monitor operation. And the exit call is like this. You have the next count greater than 0. That means you actually have some sleeping process sleeping for the next semaphore, so the next seat. And then if it is more than one, then you actually signal the next waiters. So signal the one in this room, this waiting for the doctor's room. And if not, then that means that there is nobody waiting in there, so we wake up the general public. And this is the mutual exclusive part. It will be this empty entry set. So that's the 3 set we have. So these are the entrance call and the exit call to a monitor using semaphore. We actually have this entrance call for mutual exclusive, the signal call or the exit call for the semaphore mutual exclusive, and we also have a mutual exclusive. We also have the exit call for the next queue, and the next queue can have 0 to many different, many number of the, as many as possible number of the waiting set. So this signal can be many. If it doesn't wake up the mutual exclusive, it actually will wake up the one in the mutual exclusive set, and then you got +1. So somebody would enter into the waiting queue. So if there is no wake up call, you don't have the signal call, then actually you a lot of the queue, and if there is nobody waiting, and if there is somebody waiting there, we will wake up this one in the waiting queue. So P of X is equal to wait, and V of X is equal to signal for the semaphores. And actually we have 2 different kinds of semaphore, one for the next queue, one for the mutual exclusive access. So to implement the monitor using semaphore, if we have a synchronized method like this, it will be compiled to the following thing. The data structure will have the semaphore mutual exclusive, semaphore next, and the integer count, next count. And the integer next count equals 0. And then for this synchronized method, we will put the entrance call here, the exit call here, and then you put your function body over here. So this part is the P function for the monitor, and this part will be the V function for the monitor. So for the real application, we can have a instant synchronized method like this, or this. These are 2 ways to write it in Java, and we use the synchronized method in class. Mutually exclusive access in the method, wait and notify are available in the synchronized method, and this wait and notify actually are this section and this section for P and V. So when we implement the bounding buffer case, we have a buffer, we have the count in and out, and we actually initialize the bounding buffer with certain size. And then we have the put, this one is the producer, get, this one is the consumer, and we put a weight and signal pair right here and here. And this weight, when you implement with the semaphore, this will actually be behaving like the semaphore way. But if you have this synchronized method for the Java monitor, this wait and notify pair will be behaving like the monitor case. So they will be implemented like this, the P and V function here. And actually, in the background for the monitor, we have this data structure as well. So that's the way that Java is implementing the bounding buffer for us. And actually, the notify and wait are the P and V function. Sorry, the wait and notify function are the P and V function for the monitors. And the monitors can be implemented by the semaphores. And a synchronized class method is like this. Instead of putting this, you put myClass.class. And this is equivalent to static synchronized void my method. So we have told, and so here I have shown you the instance synchronized method and the class synchronized method. Monitor feature, Java has built-in monitor feature. C don't need to use pthread library, and pthread library is available for Linux. Condition variable, let's look at the condition variable implementation. Condition variable, it is improved from semaphore with thread in queue. Semaphore had limited number of seeds. Condition variable has a queue, so it has a flexible length of the queue. Consider an operation system. An idle request from a user program via a system call may not be completed immediately. Say we try to write something to the disk, and the writing head may be waiting for different process to finish. Should this happen, the operation system may postpone this I/O service and serve another user until the I/O operations completes. Then the operation system will resume the I/O service for your program. In this case, the user feels that he is blocked within the operation system. For a similar reason, a thread in a monitor may have to block itself because its request may not be completed immediately. This waiting for an event to occur is realized by condition variables. So condition variable is to implement the waiting for events. Condition variable, a condition variable indicates an event and has no value. It has no value, it only has the methods. More precisely, one cannot store value into nor retrieve a value from a condition variable. If a thread must wait for an event to occur, that thread waits on the corresponding condition variable. If another thread causes an event to occur, that thread simply signal the corresponding condition variable. Thus, a condition variable has a queue for those threads that are waiting the corresponding event to occur to wait on. And as a result, the original monitor is extended to the following. The private data section now can have a number of condition variables, each of which has a queue for thread to wait on. So basically, we can have a monitor, and a monitor actually is guarding on the mutual exclusive access for a certain class. And we can add some conditional variable to there, and conditional variable has its own queue. And these conditional variables can be used to monitor the conditions for the I/O channels. For example, we have a monitor on certain data set, and we have the I/O channel condition variables. So each control variable is associated with a resource, usually maybe it's I/O or disk. A monitor class is a resource. The condition variable works like semaphore, except that it has a queue. So the length of the queue is flexible, but semaphore has fixed number, which it is specified by the capacity. And other than that, it is similar to a monitor class. So right here, I show you the diagram for condition variable by semaphore, and you have shared data, and you have queue associated with the SY conditions, and you also have a queue for the monitor entries, and you have operation and initialization code. So it is similar to monitor or thread or event queue, and you can declare condition variable X and Y. Two operations on a condition variable. You have the wait and signal similar to the semaphore, except that they have a queue. So their waiting set is undefined, can be 0 to as many as you can. So x.wait is a process that invokes the operation to be suspended. X.signal resume the process that invoked by. X.wait. And here is the implementation for the condition variables. We actually have a condition variable, and then we have semaphore, sem, and integer count. These are the data structure need to be associated with a condition variables. And then we have a wait function like this and signal function like this. This is the P function and V function for condition variable. Remember that it can also be implemented by semaphores, and it would achieve the wait and signal function for condition variables. And condition variable can have a queue, and these are similar to the monitors. And you can actually implement a monitor using condition variable with such data structure and with such wait and signal function and declaring a variable conditions. Implement monitor using condition variable is just like using the semaphore, except it has a queue, and the wait and signal function are like this, and adding the data structure in there. Lecture 10, Language Level Mechanism, Part 2, Condition Critical Region. What is conditional critical region? Conditional critical region, CCR, are another alternative to semaphore. A critical region is a syntactical delimited critical region. A conditional critical region also specifies a Boolean condition which must be true before control will enter the region. So we have protected variable and a Boolean condition. Once the Boolean condition is met, then we enter into the critical region. So compare with the semaphore actually checking certain condition or the number of seeds to be met before you go into it, and you have a class or something that is actually being accessed by the monitor. And semaphore don't have this protective variable, but this is similar to somewhat to semaphore or the monitor. No thread can access a protected variable except within a region statement for that variable. Regions can nest, though, as with nested monitor codes. The programmer needs to worry about deadlocks. So you need to take care of the deadlocks in using the conditional critical region. So right here we have an example of using the conditional critical region for bounded buffer, and it is quite straightforward. We have the same record, same setting for the next full and next empty, and same setting for the floor slot. So right here, when we check on the protective variable buffer, that is a Q, and then we check if the full slot less than size. That means you can still insert the data, so you get enter into here. So in conditional critical region, you don't have the signal weight and signal pair. Instead, it is implemented by a region statement. Similarly, for this remove function for consumer, and you have the access condition and protective variable set up like this. But the algorithm is similar to semaphore, monitor, or conditional variable. Right here, we show you the critical condition. Right here, we show you the conditional critical region and a statement right here that is called atomic. And when the condition is met, you go into the statement. This is quite simple for the pattern. So wait until condition is satisfied. Execute the statements automatically. And right here, we have this get function for Q. If the items not equal 0, then we decrease the number of items and get the data out. This just like the popping of a stick or getting an item out of a buffer. The implementation of conditional critical region can be done by software transactional memory, and software transactional memory will be covered later in a separate lecture. Right here, I just show you it can be done by this software transaction memory. Use all traditional STM command and STM wait, like implementation of monitor using semaphore. Implementation of conditional critical region can use software transitional memory as M. So the statement right here, you put a condition right here and statement right here, and this will be the implementation for this CCR, the conditional critical region. So you have the condition map and you go into there, and since this statement can be done, so we actually make sure that the transaction is committed. Otherwise, if the condition not met, then we wait on the condition to be met. And if there is an exception, for some condition you wait, then you wait for it until it is done, you store the T. And actually this storing T will be handling some exceptional condition that may happen to your conditional critical region. Language level mechanism part 3, synchronization in Java. We have a complete video tutorial over this website. I have these tutorials and it is free for you, and you can come to this chapter and you can come to this tutorial, but somehow I have not finished this tutorial completely. So if you go there and didn't find all the lectures and quizzes, you can just wait, and actually I will make it up soon. And actually for the time being, it probably only has 3 lectures, and I plan to go for 13 lectures for this tutorial. Synchronization in Java, we have thread, future, and callable classes, and the related pools. And we have semaphore class and the new condition class. Semaphore is for normal semaphore, and new condition is for condition variable. And we have lock, re-entering lock classes for mutual inclusive lock. And we have semaphore using semaphore class, monitor design using the synchronized keyword for lock variables, and we have conditional variable. We have condition variable using new condition class. So apparently, most of the mechanism being implemented in Java. Core example, we have the critical region. We use the synchronized method, and we actually put the object over here, and this become a critical section. And we can also use the lock variable by declaring a lock. And we have the lock and unlock pair. This just works like the mutual exclusive access control for lock and unlock. And we have semaphore. You can declare a semaphore, but the semaphore will have the acquire and release. This is different from the traditional name of PV or wait signal pair. The name for semaphore methods actually are acquire and release. For example, for condition variable, you can declare a condition, then you have the condition wait and signal statement like this. And if you want to build a monitor, you can have a simple monitor, and you have the lock, unlock using the re-entry lock, and you can replace the lock, unlock with the semaphores acquire and release, or condition variables wait and signal, and or you can also use the monitors synchronize the critical section like these statements. The instant synchronized statement that can also implement for the monitors. The Java memory model specifies exactly which operations are guaranteed to be ordered across threads. It also specified for every pair of read and write in the program execution whether the read is permitted to return the value written by the write. A Java thread is allowed to buffer or reorder its writes until the point at which it writes a volatile variable or leave a monitor. At that point, all its previous writes must be visible to other threads. Similarly, a thread is allowed to keep cached copy of values written by other threads until it reads a volatile variable and enter a monitor. At that point, any subsequent read must obtain new copy of anything that had been written by other thread. So Java memory model actually rely on the cache coherence model, and actually some variable can call as a volatile variable, and we need to take care of it. The Java memory model, the compiler is free to reorder ordinary reads and writes in absence of intra-thread data dependence. If the compiler can prove that a volatile variable or monitor isn't used by more than one thread during a given interval of time, it can reorder its operation like ordinary accesses. Volatile is related to write-back scheme. So basically, this is how the Java memory model is implemented. Now, let's look at the language level mechanism, part 4, transactional memory. Transactional memory, the software's transactional memory is used to implement the conditional critical region. Software transactional memory, actually software means the algorithm, transaction means data baseline, and memory means data access. So you actually have the algorithms for data baseline, data access to your memory, and database like means you had a mutual exclusive access to the database, and same thing for the memory. And we have the software transaction memory as the protocol to access a memory with the mutual exclusion. So HTM usually is a language extension or API framework. It is just like another concurrent control mechanism like lock, actor, semaphore, condition variable, or CCR. So SDN is another protocol. ACID. For database, we have this word ACID. A for atomicity, C for consistent, I for isolation, And database require your read or write to be atomic. You cannot break it. And data need to be consistent. And the critical region need to be isolated. And also the data need to be durable. So it has the durability. But for STM, since we are not saving the memory back to hard disk, it is only in memory, so we don't have a durability issue. So not for database, it is actually for memory transaction about this red cross. So this red cross is not for database, it's for STM. So transactional memory used to implement conditional critical region. Transactional memory attempt to simplify concurrent programming by allowing a group of load and store instructions to execute in an atomic way. So basically, this is a load store operation that actually means is handling the CPU and the memory. It is a concurrency control mechanism analogous to database transaction for controlling access to shared memory in concurrent computing. Transactional memory system provide high-level abstraction as an alternative to low-level thread synchronization. This abstraction allows for coordination between concurrent reads and writes of shared data in parallel system. Hardware transactional memory. We have hardware transactional memory just like the cache and database. And actually, this is a special hardware. You have the on-chip connection bus or network, and you have the data cache, and you have the concurrency, and then you have the coherence request, and access the transactional memory register, user register, and register checkpoints. So basically, this transactional memory can be implemented by hardware. But how transactional memory works, we will look at the following slides. A simple idea to think about transactional memory is like this. You have the hardware transactional memory, you have transaction routine, you have transaction runtime, and you have throughput cache and shared memory. So these actions are working on the cache, and cache will have the coherence problem with memory. And similarly, for software transaction memory, the function or algorithm you talk about is transaction descriptor. And the records that before writing into certain object is called ownership record, and it is similar to cache. And the shared memory for software, it is actually application heap. Transaction memory management, you have this method, STM start, that will begin a transaction within the executing thread. STM abort, that will abort the transaction progress by the executing thread. And actually, this is write miss. When you try to write something to the memory location, and actually you cannot hold a variable or record to write it, then you will have STM abort. So this actually is write miss or wait signal. And we have the STM read and write. These are two transactions. And we have STM commit. And this commit means write hit. That actually will attempts to commit the transaction in progress by the executing thread, returning true if it succeeds, and fail and false if it fails. Software transaction management, we have STM validate. This is a Boolean function, and you will return whether the transaction will be validated or not. It indicates whether the current transaction will be able to commit to be executed or not. That is, whether the value read represent the occurrence and the mutually consistent snapshot, and whether any location updated had been subject to conflicting updates by another transaction. STM wait, that sleep and wait on signals, and STM wait would be equivalent to STM abort, leading to caller spin spinning, waiting. In our implementation, STM wait blocks the caller until an update may have been committed to one of the locations that the transaction had accessed. So STM wait is similar to the STM abort. So wait is more popular term actually. And right here is a pseudocode for STM system. And instead of reading this pseudocode in detail, let's look at one example. So right here is a simple STM transaction. We start the STM service and read value. And if we can write, we check the STM validate. So this actually is the wait signal. If it is validated, then we go in to do the transaction and perform the STM commit. And if it is done, then we break. And this break will break the whole loop. So right here, we have the application heap. This is like main memory. We have these records over here. And we do a pairing algorithm with this. So we have the ownership records, and ownership record is just like a cache. And this cache will keep track of the current versions for each of the record. And one of the record may have 2 entries. And then we have a transaction descriptor 1. This is a transaction that will make modification on the ownership record. This work like cache. And the other one, we have application heap. This work like memory. So we have 2 transactions. We will modify the A1 from value 7 to 7 and version 15. And we will modify A2 record with version 7 from 100 to 300 to, and that 300 is version 8. So basically, we decided these 2 will be modified. And then we commit it. And then we commit to modify it. So the value for this heap, for this record A2 becomes 300. And the version being updated to 15 and 8. And when will the abort happen? So we are trying to commit the write to these 2 records. And if at the same time we have the transaction descriptor 2 also request to make the modification, then this same version 8 won't go through. So A2's ownership record is unavailable, and commit, fail, and abort. So this one will be waiting. And STM collision, when you have the STM collision, you have STM abort or STM wait, then we will be waiting. And actually this time, for example, we had such A1 update and A2 update, and we have this transaction sharing the same destination. So this one actually will be kicked out. So this program failed my CCR condition, so I aborted and fell asleep. And then this part 1 committed to update the memory for location for A1 and A2. And for description, for transaction descriptor 2, it will be waiting because it is locked up by some other process. And when we optimize it, we can move up to here. So basically, we have A1 transaction that is committed to this A1, and for the value from 7 to 7, stay from 50 to 50. And A2 will be related to this record, and actually it will be modified from 100 to 300. And we have the A3 transition that will write this A3 from 200 to 8, and the version updated to from 8 to 9. But this is inconsistent with the A2 transition. So we actually can optimize it by stealing the original record from this descriptor 1 to move down to descriptor 2. By this way, this transition 2 can still be used. And STM and HTM parallel the data copies. So here are the relationship between the HTM and the HTM and STM. Now we are on the last lecture for chapter 13, language level mechanism, part 4, other topics. The first other topic, implicit synchronization. Actually, this is an isolated topic, so we will go on this first. In several shared memory languages, the operations that threads can perform on shared data are implicit rather than explicit operation. That means you have some language structure and you will initiate several threads instead of having the explicit operations to call the threads or initiate the thread. For example, the for all loop of HPF and the Fortune 95. For all loop, each iteration reads all data used in its instance of the first assignment statement before any iterations updates its instance of the left-hand side. The left-hand side updates occurs before any iteration read the data used in its instance of the second assignment statement. So basically, if we have a for all loop and then we process several additions for each of the array element pairs, so x1 will plus with y1 and produce the result of g1, we have such vector processing for each of the elements in X array and Y array. But our processor can handle up to 4 in parallel, so each time we need to have one block being processed. So initiating these threads are implicit instead of explicit operations, and explore the maximum vector parallelism in dataset, processing unit, and compiler technology. Dependency analysis plays a crucial role in other language as well. So basically, you have to count how many threads can be run in process, and that we can unroll your loop in the for all loop, so that in a way that will explore the maximum vector parallelism. And this is done implicitly. The second topic I'm going to talk about is the future. But before we touch this topic, let's look at something else. For those of you who did not sign up my concurrent programming course for Java, please do so, because there is a lot of very important information. Before we move on to the future, let's look at a thread class. A thread class is a miniature for a thread. And in the thread, we can put in a runnable object, and this runnable object actually can have a run function. So this thread will run on the function that's specified within the run method. And this is how we manage the thread class and having it to do some calculation. So the idea is you have a thread, but the task you want to perform should put in this run function. And this run function will start when somebody call the start function in the thread manager. And the thread manager is a container that contains the runnable object, and the runnable object carry the code. And there are several different methods to be used for a thread. And this thread option can work on several different functions as long as you put different functions into the run function. And the thread can also perform the fork and join operations. So basically, you can create certain thread, and the thread itself can fork some process if you actually initiate a new thread inside a certain thread, and you initiate this new thread, thread 4, and you get started with the over there. And at a certain point, you can join the thread 4 into the main thread. So that will be joined over here to finish this one and go back. And thread also control the states of the thread. For each thread, you will have the run state, a ready state, a running state, and the wait states. Let's return to our slides. Thread is related to our topic for future. Let's move down for a couple of slices. Let's look at this first. The thread is a wrapper for runnable object, and runnable object actually has a run function but have no return value and no exception. And you can have a version that is callable. A callable object has a return value v and can throw the exception. So that's a different version of the runnable object. We call it callable. So when you call, you have the return value and can throw exception. But if you run, that has no return value and no exception. And the wrapper for callable object is called future, and the future actually will return some value that is passed from the callable object that will be put into the future task. And the relationship of the callable and future is the following. You have the runnable interface, and you have the future that is the interface, and you also have a runnable future that combine these two interface, and then you have future task. And future task can call a runnable or callable. So actually, future task is the concrete class that can call runnable and callable. And thread, you can only put the runnable over there. So that's the difference. So future, important point, future and future task in Java. Future is a base interface defined abstraction of an object which promises result to be available in the future, while future task is an implementation of a future interface. A future is a parametric interface, and the type safe written as future v, and v is the value that you can return, and actually that will get from the callable object, and callable object is the method wrapper for future task, and future provide get method to get a result from this for this v value, which is a blocking method and block until the result is available to future. Future interface is also defined. Future interface also define cancel method to cancel task. So future actually is a manager for the task, but future is an interface, the real manager object or class or concrete class is the future task. And you also have the is done checker, is cancel checker, something like that. So let's look at the future and callable in our Java language. So this is in my tutorial. And the difference between runnable and callable, callable is parametric. You can put different type over there, and that type actually is the value that you will return when you call. And the call function is similar to run function, except that run function, you put the call in, but you don't return value, but call function, you can return the value. And then runnable cannot throw the exception, and callable can return the exception. So right here, we have one thread that implement runnable, and the run function just print out Java welcome or well. And over here, you actually can throw the exception, also had a return value, and that will be returned in the string format that is callable with the type variable string. So right here, we have this same summary page. Let's move on. And callable is runnable in multi-threaded procedure. Callable is multi-threaded function, and runnable is a multi-threaded procedure. That's the difference. And future is the object. Future object is a handler for runnable and callable objects. So future or future task can carry runnable and callable, and thread can only carry runnable. So future is an interface. Usually it is not directly used. Runnable has limited capability. Future has method to receive the value called .get. Future has a method to check the executor is done or not. Future has method to cancel its executor. Future has a method to check if the executor is canceled. Future is combined with runnable and runnable feature to have complete features. Future can submit a runnable executor, work like fork. And future, you can run and get value and return. So runnable future and the future's relationship are here. And string worker is for the string AWT package. But these are not covered in this chapter. But basically, you can see future task will be able to run runnable and the future, and it is the concrete class. And I is actually the interface. And this is the environment for runnable and the future and the executor. And these are the detailed framework for executor framework interface. I don't want to go into the detail for this, and this is part of the tutorial. Let's return to our slides. So roughly say, callable and runnable are methods these callable and runnable are interfaces that can have the methods that carry the call, and call function has the return value, and future task and the thread are the carrier or the wrapper for callable and the runnable. And future task can wrap up callable and runnable, but thread can only wrap up runnable. So the future in multi-Lisp. Implicit synchronization can also be achieved without compiler analysis. Future construct a dialect of scheme So by future, actually, you have some function and arguments, and actually you branch out a certain thread. It is called future, and future is semantically neutral, assuming all evaluation terminate. A program behavior will be exactly the same as this, except that it is branched out as a separate function. In the implementation, future arranged for the embedded function to be evaluated by separate thread of control. So it has a separate thread. So you have a parent process, you have one child function, second child function, you put into two future wrapper. So these two actually run as parallelly, and then the parents will join them together. There were no additional synchronizations mechanism in multi-lisp. Future itself was the language-only addition to scheme. And future in C#. In C# with parallel fx, we can use future to create a task. And this future has a lambda expression, that's the function being put in. And after it finishes, it will return the value to discretion. So same thing for this number in stock. It calls this function, and the value will be returned to number in stock. So these are future functions, and we actually will get the value once the process finishes. And static future is a factory. It creates method support generic type interface inference, allow us to pass delegate compatible with function T. So you actually can put certain function in there. Something like lambda expression is okay. For T, we have specified the delegate here as lambda expression. If get discretion return a string, discretion will be type future string. If get inventory return an integer, number in stock will be type future integer. And we have done this. And we have done this as well. And we have done this as well. So future is important point for future and future tasks in Java. Future have 4 sub-interfaces, each with additional functionality: response, runnable future, runnable scheduled feature, and the scheduled feature. So these are different type of features. Runnable feature also implement runnable, and the successfully finish of run function cause completion of this feature. Future task and swing worker are 2 well-known implementation of future interface. So these 2 are concrete classes that implement the future interface. Future task also implement runnable future interface, which means this can be used as runnable and can be used as callable as well, and can be submitted to executor service for execution. And executor service is a pool of runnable object or task. Though most of the time, executor service create future task for you. For example, when you submit callable or runnable object, you can also create it manually. Future task is normally used to wrap runnable or callable object and submit them to executor service for asynchronous execution. So future task is a wrapper and can submit this function to the service, and the service is a pool to allow you to accept several runnable or callable object over there. Topic, we are out of the future now. Topic, parallel programming, parallel logic programming. There are 2 strategies for the backtracking, searching of logic language, such as Prolog. It's also amenable to parallelism. One is end parallelism, the other one is or parallelism. The fact that the variable in logic, once initiated and never subsequently modified, ensure that parallel branches of an end cannot interfere with one another. So basically, in logic processing, in logic programming, we have end parallelism, so you can run several end at the same time. And you can also have or parallelism, so you pursue alternative solutions in parallel. because they will generally employ different unification branches, or branches of an OR must use separate copies of their values. So this is the parallel logic programming. Basically, you can pursue two types of parallelism in logic programming. AND parallelism and OR parallelism create new threads at the alternating level. OR parallelism is speculative. Since success is required on only one branch, work performed on other branches is in some sense wasted. So actually, or you have to, or sometimes would over execute it because it would waste time on something that is not necessary. All parallelism work well, however, when the goal cannot be satisfied, or when there is high variance in the amount of execution time required to satisfy a goal in different way. For example, you cannot predict the execution time of a certain branch. Both AND and OR parallelism are problematic in Prolog because they fail to adhere to the deterministic search order required by language semantics. Prolog, which supports both AND and OR parallelism, is best known as the parallel Prolog dialect. Message passing. Message passing is not covered in this book, but message passing is more useful in multi-programming, and shared memory model concurrency is more useful for multiprocessing. For a program in the same computer with a shared model for different processes. But message passing is better for different programs to share the data or perform the synchronization. Shared concurrency is becoming ubiquitous on multi-core processor and multiprocessor servers. Message passing still dominate in both distributed and high-end computing. Supercomputers and large-scale clusters are programmed primarily in Fortran or C++ with the MPI library package. MPI means Message Passing Interface. Distributed computing is increasingly relies on client-server abstraction layered on top of libraries that implement the TCP/IP Internet standard. As in shared memory computing, scores of message passing language have also been developed for particular application domain or for research or pedagogical purposes. And we are not spending a lot of time on this message passing. Thank you, and this concludes our chapter 13 and also conclude our discussion on this textbook for our 8-week course. I really appreciate your participation on this course. Thank you, and I'm looking forward to have a chance to be with you sometime for other courses. Thank you. Bye.